Pittsburgh. Go Penguins. He's the LMS speaker, keynote speaker in discrete mathematics. Well known, among other things, for the computer-assisted proof of the Kepler's conjecture. And today he's going to talk about the formal proof of Kepler's conjecture using Hall light. Thanks.
It's my pleasure to be here today to talk to you about the formal proof of the Kepler conjecture. I want to start out by thanking my many collaborators and the paper of 23 co-authors. I especially want to thank those from the UK, Mark Adams, John Harrison, and Roland Zoomkeller is working here in London now. And Alexei Solovyev and Oleg True did a lot of the computer implementation of what I'm going to talk about today. So I'll start out with a few pictures about what it is that we're doing. We want to pack oranges as densely as possible, so we want to know in what arrangement the greatest fraction space is filled. So the answer is the face-centered cubic packing. That's this arrangement of oranges we see here. So this whole talk will be a justification of why this is the densest possible. This picture shows a triangular-based pyramid of oranges and a square-based pyramid of glass. And you might ask which arrangement gives the higher density. And the answer is both give exactly the same density. And the reason is that they're really the same lattice, the same arrangement, just cut in different ways. You see in this small picture on the left that you can insert the triangular-based pyramid into the square-based one, and it's really the same crystallographic structure, just at different angles. So they have exactly the same density, about 74%. So the study of packings goes way back. This is an early Sanskrit source from about the 4th century, giving a formula for the number of balls in a pyramid as a function of the number along an edge. And if you translate it in the formula into modern notation, you get the number of balls n along the edge. In the pyramid, there'll be n times n plus 1 times n plus 2 over 6. Or equivalently n plus 1 cubed minus n plus 1 over 6. And here is a possible explanation of how they might have found this formula a long time ago. If you take the pyramid and make them into cubes and push them all to one side so that they line up in columns, then this formula n times n plus 1 times n plus 2 over 6 could be interpreted as the number in a rectangle but divided by 6. So we assemble 6 of these puzzle pieces together into this rectangle to justify the formula, or we can also arrange them into a cube minus the diagonal to justify the other formula. So there's a simple proof of this formula for the number of balls. Thomas Harriot was Sir Walter Raleigh's mathematical assistant, and Raleigh, for his warships, wanted formulas for a number of cannonballs, and he assigned this task to Thomas Harriot, and this is the solution that Harriot found. He used Pascal's triangle. So if we look going down, the entries here are 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. These are just the entries of Pascal's triangle. And then down the diagonal, I've drawn 0-dimensional packings, and then 1-dimensional packings, and then 2-dimensional packings, and 3-dimensional packings, 4-dimensional packings. If you go to the British Library and look at Harriot's writings, you see that he actually tries to draw the 4-dimensional packings here. Take a look and see if he succeeds or not. But then you see that you naturally get, if I pack this ball on top of these 2, I get this arrangement. If I take these 4 and pack them on top of these 6, I get this arrangement of 10 and so forth. And so you see immediately that the number of cannonballs in a packing has to be a binomial coefficient. And so we get into the derivation of the formula for the number of balls. So the density of the face-centered cubic is pi over the square root of 18, about 74% of space. This slide does the calculation of the density, and it also shows why this packing is called the face-centered cubic packing. If you take a cube and put a ball in the center of every face, another ball at the corner of every corner of the cube, then again you get this cannonball arrangement, and so this gives the name face-centered cubic. And if you look, there's half a ball at each of the 6 faces, so that gives a total of 3 balls. There's an eighth of a ball at each of the 8 corners, so that gives 1 more, so there's a total of 4 balls inside the cube. And so you get 4 times 4 pi over 3 if we make the radius 1. The edge is root 8, and that gives the density of pi over root 18. So that's the calculation of the density. This slide, this is just, again, this general background on packings. The face-centered cubic is not the only packing that realizes this maximum of pi over root 18. There are actually infinitely many different arrangements that have the same density. The best known other arrangement is called we've got the face-centered cubic and hexagonal close packing. Hexagonal close packing is on the right. You see it's again made out of hexagonal layers in the same way, but there are actually 2 ways to set a 3rd layer above. So here, notice that the triangle below and the triangle above are rotated with respect to each other. And in hexagonal close packing, the triangle above and the one below are aligned with each other. So it's clear they have the same density, but they're actually different crystallographic structures. And so the proof of the Kepler conjecture is not going to have any sort of strong uniqueness statement because there are so many different arrangements with the same density. The problem I mentioned was studied, packings were studied by Thomas Harriot between 1600 and 1610. Thomas Harriot and Kepler had a correspondence on the subject of optics. Thomas Harriot was interested in packings because he was a believer in the atomic theory. He thought the properties of nature could be explained by packings of spheres. Kepler was more skeptical. He didn't believe in the vacuum. If you had atoms, what would there be between the atoms? But eventually he was somewhat persuaded by Harriot and wrote a book called The Six-Cornered Snowflake that today we would see as an early book in crystallography, trying to explain why the number 6 comes up in nature regularly. And so in this booklet, he writes that the face-centered cubic packing is the tightest possible, so that in no other arrangement could more pellets be stuffed into the same container. And it's this statement that gives us the name of the Kepler conjecture. So Kepler, in his booklet, the booklet is called The Six-Cornered Snowflake. He was trying to explain why snowflakes have 6 sides. The idea of density was suggested to him by the study of pomegranates, seeing how tightly the seeds were packed in. And then he looked at thinking of the number 6 in nature. He turned to the honeycomb, and looking at the structure of the honeycomb, if you look at the base, so that here I've shown a 3-dimensional picture of honeycomb cells. You get in the base, you get rhombic faces, and here again is the base of a honeycomb cell. And if you repeat this pattern. So if you seal off the top of the honeycomb cell in the same way that the base is sealed off, then you get what's called a rhombic dodecahedron. It's a 12-sided polyhedron with rhombic faces. And in the same way that the honeycomb cells fit together, this rhombic dodecahedron tiles space. And if you put a single ball inside each of the cells, and then strip away the cells, you're left with an arrangement of balls, and you get exactly the face-centered cubic packing. So this apparently is how Kepler went from the study of the honeycomb to arrive at the structure of the face-centered cubic packing. Eventually, this problem was recognized as a mathematical problem that needed to be solved. Hilbert made this part of his famous list of problems in mathematics in 1900. It became part of the 18th problem. Rogers quite famously said, many mathematicians believe and all physicists know that this arrangement is best. Milner, writing about Hilbert's 18th problem, said the problem in 3 dimensions remains unsolved. This is a scandalous situation, since the presumably correct answer has been known since the time of Gauss. All that is missing is a proof. Gauss was the first to really make a serious contribution to this problem. He was thinking of this in terms of quadratic forms, but what he proved shows that if you restrict to packings that are lattices, so the centers of the spheres all line up on points of the regular lattice, and under this special assumption, then the face-centered cubic packing is the best. Working with a graduate student, Sam Ferguson, we announced a solution to this problem in 1998. The proof was long and fairly complicated. The proof itself, the text part of the proof is about 300 pages. And the computer parts of the proof were many tens of thousands of lines of computer code that were specially written for the proof. And the computers at the time, was in 1998, but it took months of runtime on computers to go through all of the calculations needed for the proof. So, here are a few of the calculations. Maybe it's a little bit small to see, but as part of the proof, we had hundreds and hundreds of nonlinear inequalities that go on for pages like this, and this, and this. So maybe you could think for a minute about how you would go about, first of all, organizing hundreds of inequalities into a long mathematical proof, and then how you would prove those and then justify to the referees that you really got proof of this long collection of inequalities, and these are just what you need to give a proof of the Kepler conjecture. So the proofs of these inequalities were done by a computer. These are all inequalities that involve a small number of variables that can be expressed in terms of simple algebraic functions and square roots and trigonometric and inverse trigonometric functions. So the functions involved are not terribly complicated. Most of them are analytic functions, but in the end, the proofs were done using computer, but at floating point, but we want to know that the round off errors don't invalidate your results. And so we used what's called interval arithmetic. Instead of representing everything as a single floating point number, we give a lower bound and an upper bound. And then whenever you do additions and multiplications and so forth, the width of the interval grows to accommodate for the rounding errors on the computer, so that you're always rigorously bounding above and below all the results. And then we had automatic differentiation routines set up to expand these in Taylor series, and using the bounds on Taylor formulas, you're able to give rigorous lower and upper bounds, and then those is all done automatically in the computer using the interval arithmetic to give rigorous upper and lower bounds on these nonlinear functions. And in every case, we're able to get the asserted bounds. Okay, so that's roughly how one piece of the proof was done. And some more. So then we sent it off to the referee for checking, and I thought that my part in the process was complete. It was quite wrong. This is a statement by Jeff Ligarius, who eventually became the editor and referee in charge of the project. When this was submitted for publication, the editors organized a seminar where they invited, eventually there were 12 referees for this paper. They invited all the referees to the seminar, and I gave lectures for a week on the proof. And at the end, the referees gave me encouraging news, saying that everything looked pretty good. This was in January. They said it was until summer. In the summer, they said we're 99% convinced it's correct. Give us a little more time. And then this went on year after year. Each year they came back and said, this looks fairly convincing, but give us some more time. And eventually, the referees became exhausted, and the paper was published. So this is what Ligarius said. It's very unusual to have such a large set of reviewers. The main portion of the review took place at a seminar at Edfest University Budapest over a 3-year period. Some reviewers made computer experiments and a detailed check of specific parts of the proof. This process, detailed checking of many specific assertions, found them to be essentially correct in every case. The result of the reviewing process produced in those reviewers a strong degree of conviction of the essential correctness of this proof approach. Excuse me. So notice there are a lot of sort of weasel words in this report. It's conviction, essential correctness of the proof approach. So they're not saying they've checked it to be correct, but they believe the approach to be essentially correct. So McPherson, one of the editors of the Annals, sent me this email. The news from the referees is bad from my perspective. They have not been able to certify the correctness of the proof, and will not be able to certify it in the future because they have run out of energy to devote to the problem. This is not what I had hoped for. And then he goes on to say that we're going to have to get used to this in mathematics. So in response, the Annals created a new policy for computer proofs. There were other computer proofs that were submitted to the Annals around the same time, and they decided they needed a general policy. And in this policy, they decided they were not going to try to check the computer code. Rather, they would just look at the general methods that are being used by the people who write the code, see if the methods seem all right, and if so, papers can be accepted for publication in the Annals. Now, anybody who's been involved in computer proofs knows this is very dangerous because you can put whatever you want in computer code and say whatever you want about the methods. And if the referees are not reading the code and checking the details, then all sorts of things can slip through. So I became very frustrated with all of this, and I sort of made it my goal in life to remove referees from the process. So we once thought of computers as a human occupation. We once thought of referees as a human occupation, but that's all passed. So I became involved, this is during the refereeing process, 3 years into the process. I went to a conference in formal proofs in Vienna. This is when I became involved in formal proofs. So a formal proof is just take the axioms of mathematics and the basic rules of logic, and you put them into a computer, and you don't allow anything out until it's been checked all the way down to the foundation. So you want to prove a theorem, and the computer has to check every single step of the proof using allowed rules of logic. You can't say, you work one case and the other cases are similar, and things like this. Every detail really has to be checked. So this is the system that I used. It's called Whole Light. It's implemented in the Objective-Camel programming language. John Harrison did this while he was a graduate student at Cambridge. It's a lightweight system. In 3 slides, I can show you the whole kernel of the system. It just takes, so this is based on simply typed lambda calculus. It's a very simple system. There are just 3 mathematical axioms. There's an axiom of infinity, there's an axiom of choice, there's an axiom of extensionality. They're just 10 rules of logic saying very simple, intuitive things like equality has to be reflexive, equality has to be transitive. If you have 2 equal functions and you apply them to 2 equal inputs, then you have to get equal outputs. So I won't go through all the axioms and rules of logic. It's a very simple system. It's designed to really be an airtight system, so that you cannot create theorems except by the rules that are given to you, the rules of logic. So this is enforced by the module system and the type system of Objective-Camel. So the rules that allow you to create theorems. So there's a type called theorem, and constructors for that are hidden inside the module system. And so unless you use the rules of logic, you just can't create a theorem. So this is, I won't go through all the details of the system. You might ask, how do we know there wasn't a bug in the kernel? Because if there's a bug somewhere in these 300 lines of code, you'd be able to prove anything. To prove that polite does not have any bugs, of course, these proof checkers can be used to prove and check mathematical theorems, but they can also be used to check the correctness of code. Polite itself is a piece of code, so you can use whole light to check that whole light does not have any bugs. Of course, you run into problems with Dribble's incompleteness here, but you can add an extra axiom of a large cardinal to then give a rigorous proof inside whole light that the implementation of whole light does not have any bugs. Well, you say, well, okay, so if it has a bug, maybe it's using a bug to prove its own consistency. Whole light isn't the only proof system. There are a number of these systems that are used for proof checking. Another one is called Whole Zero, it was developed by Mark Adams, and they're automatic. He's developed an automatic translation system for proofs in one system to another system, and this proof has been automatically translated into another proof checker and checked there. So both of them would have to have a problem. And it's been also done, this work has also been done and extended in the KKML system developed at Cambridge. So at this point, I think it's fairly believable that there are no bugs in code. Next few slides, I just want to say a few words about why I think these proof assistance and proof checking is important for the progress of mathematics. So one reason is that there are a lot of long, complicated proofs in mathematics. Kepler conjecture was a long, complicated proof, but there are many, many others, and the list is growing all the time. Here I've just taken a few from a wiki page, giving a list of long mathematical proofs. It gives, of course, things like the classification of finite simple groups, which is just the all-time record for the longest, the most complicated proof in mathematics. But when I went to this list, I quite like it because it also has my thesis advisor, Langmuntz, on the list. And an academic brother, Jim Arthur, is also on the list. And various people, my work on honeycombs relies on this big paper of 1,728 pages. And Harry Schonner's work on the discrete series is close to my heart in representation theory and so forth. So there's just a lot of long, complicated mathematics, and it's just becoming increasingly difficult for people to be on top of all the proofs of all of these long results. Second reason I want to give is just that mathematics is making a transition from traditional paper-based mathematics to computer-based mathematics. This is by no means an exhaustive list. I just put up a list of a few of my favorite examples of ways that computers are used in mathematics, either to formulate conjectures or to find counterexamples or to prove theorems. So we all are aware of the proof of the four-color theorem, but very deep conjectures in number theory, such as the Burgess-Merton-Dyer conjecture. One of the clay problems was formulated and discovered the use of computers. And so a lot of this is going to have computer code with it. And how are mathematicians going to be able to verify that none of these computer proofs have any errors? So in the refereeing process, I mean, it was a long process, but at no point in that process, in the refereeing of the Kepler conjecture, did the referees ever look at the computer code, as far as I'm aware. I mean, there was just no, they let me know in clear terms that that was not part of their responsibility as mathematicians. So the third reason I want to give is just computer science itself. These same proof checkers that are used in pure mathematics are also used in implementation, checking of computer code. One example is the COMCERT project in INRIA by Xavier Dubois. It's a wonderful project, a certified compiler. And so there's a C compiler that talk about the semantics of the input and what you get down at the machine level, and you give a formal proof that the transformations done by the compiler are all justified. And at the bottom of the slide, I won't go through it, but at the University of Utah, they spent years looking for bugs in compilers, and they were able to find bugs in all the other compilers except for this one that had been formally verified. So another major computer project is the SEL4 project, a formally verified microkernel operating system. So it's to the point now where very large-scale projects can be done in computer science world, and also large projects can be done in pure mathematics. Just to mention some done in pure mathematics, Georges Gontier did the formal verification of the four-color theorem. Here he uses a structure called hypermaps to do the formalization. And then his next project, he led a team to do formalization of the odd order theorem in finite group theory. So this is the Feit-Thompson theorem was an important and critical step in proof of classification of finite simple groups. So this is only a 250-page piece of a much bigger project. But, it shows that really non-trivial mathematics can be done formally. So this is just first page of the paper where I announced the FlySpec project. The FlySpec project then is the project to give a formal proof of the Kepler conjecture. So I became frustrated with the referees. I wanted to cut the referees out of the project. So I decided, let's just do the whole thing formally. We'll have a computer check every single logical step of the proof, and then we don't have to worry about the opinion of the referees anymore. And here I say in this paper, in response to lingering doubt about the correctness of the proof, at the beginning of 2003, I launched the FlySpec project, whose aim is a complete formal verification of the Kepler conjecture. In truth, my motivations for the project are far more complex than a simple hope of removing residual doubt from the minds of a few referees. Indeed, I see formal methods as fundamental to the long-term growth of mathematics. And the reasons for this are those that I've just given to you. The FlySpec project the name comes from just taking formal proof of Kepler, so I made that into an acronym, FPK for formal proof of Kepler, and I had the letters FP and K. I looked for a word in English that had started with F and then with K. The FlySpec project. I use FlySpec in the meaning of to scrutinize and read. As part of the project, I completely rewrote the proof of the Kepler conjecture. Now, some people feel that in doing a formalization, you should be as faithful as possible to the original proof. Gontier, in his work on doing Feit-Thompson and Furcolor, did a lot of transformations of the original proof. And I have a similar attitude that when you do formalization every day, you should wake up in the morning and think, I could either spend the day simplifying the mathematical proof on a purely mathematical side, or I could spend the day on the computer doing formalization of what I already have. And I ask which is the most efficient thing to do, which will finish the project sooner. And almost always the answer is to spend more time simplifying the mathematics before going to the formalization. Formalization it's becoming more efficient all the time, but it still takes a great deal of effort to translate classical proof into a formal proof. And if you can transform and simplify the proof, so much the better. So one big simplification, I won't go into details, was we use a slightly different partition of space than was used in the original proof. There are various, if you take a point for every sphere center, there are different well-known partitions of space associated with a collection of points.